Hi. So first, let me thank the organizers. I'm very pleased to be here. We've had a great talk so far. So I'm Pierre Latouche. I'm from University Paris 1, and I'm going to talk about assessing goodness of fit in logistic regression models for networks. And this is the joint work with Stéphane Robin and Sarah Ouada from AgroParisTech. So usually I start with a long introduction on real network and models and so on, and because you're all familiar with this, I'm going to go straight to the point. So here's a series of models, random graph models that people have used a lot. This is not an exhaustive list, and the key point is that those models have been studied in a probabilistic point of view, but we also have very interesting results in statistics. So basically, if you've got a real data set, you can use these models to do the inference. You can estimate the parameters and so on, and sometimes do a bit of clustering. So in some cases, you can do exact inference, like for this very simple model, but in some cases, you might need to use variational approximations or sampling and so on. In red, you've got the stochastic block model, which is, as far as I can see it, in many cases, the starting point of a huge amount of work. You start from this, and then you add up some new features. And then more recently, this W-graph model, which has received kind of a momentum, and it's not a new model, but in the last 5 or 6 years, a lot of people have started working on this. So here's what I am interested in today. I want to study a binary network for which I have some covariate information available. So this is an example. This is a network of trees, and so ages are binary, and you've got a connection from 2 trees if they share some common parasite. So this is a given information, and also we have a set of covariates. So for this network, for each pair of vertices, we've got the genetic distance between the trees, the geographic distance, and then the taxonomic distance. So you want to consider random graph models capable of taking these 2 sources of information into account. That's basically the idea of this talk. So this is not a new subject, and many methods have been proposed, and you've got, for example, the latent position model of Pierre, and then you can put some covariates in it. Then you can also do that for the latent position cluster model if you're interested in clusters and so on. And then in parallel, some extensions of the standard SBM, stochastic block model. The extensions allow to deal with covariates. But in many cases, and we had a very nice introduction yesterday, historically, originally, sociologists have worked a lot using logistic type models. So this is the model which is given here, and which corresponds to the talk we had by Peter Hoff. So Yij here is the Bernoulli variable. So 1 if I and j are connected, and 0 otherwise. So obviously you've got a Bernoulli distribution here, and then you've got a link function. So here for this talk, this is the logistic function, but you could use also probit regression and so on. And then inside the logistic, you've got a bias term, a real number, and then a scalar product between a regression vector and then a set of covariates. So as we saw yesterday, Xij is a vector of covariates for the pair ij. And this vector is of dimension d. So, and this is a typical example that we have. So you've got Y. This is the adjacency matrix that we're going to have in the next slides. And then X can be seen as a tensor, n by n number of vertices, and then D is the dimension of the covariates. So there are many, many things associated with this, and in particular, as we saw yesterday, using such a model basically assumes that all vertices are independent. And if this was the case, that would be a pretty nice model. So how do you use it? In practice, you've got your data, and then you run your favorite GLM optimizer, like if you're a frequentist, you might use like Newton-Raphson or something like that. And if you are Bayesian, probably you would use like the expectation propagation, which is probably one of the best algorithms for logistic regression. And then you would get your result, and at the end of the day, after estimating your parameters, so namely beta and alpha, you might want to ask the question, how good is my model? Does my model explain the data? And as we're going to see slowly through this talk, the key question here is we're going to assume that we can add up some covariates as we want. So we have a network, some covariates, and then we add up some new covariates, and at some point you want to say, do my covariates explain entirely the construction of the network or not? So that's pretty much the key question. That's not an easy question, and to do that, we're going to use two models which do not use covariates. So we're going to use the stochastic block model and the W-graph model. So the stochastic block model, very quickly, we had nice introductions yesterday on this model. So this is, for me, a mixture model for graph. So for each of your vertex, you associate vertex I to a latent vector or latent variable sampled from a multinomial distribution. So basically, each point is going to be associated to a cluster. So you've got pi here, this is a vector, and this is the probability of being in each cluster, cluster 1, cluster 2, and so on. So you sample in a generative perspective, you sample the latent clusters, and then knowing the cluster, you sample the edges. So this is a product here. So if this is equal to 1, it means that I is in cluster K and J in cluster L. And if this is the case, then you sample an edge between I and J with a probability rho KL in this log. So very easy to sample, a little bit harder to do the inference, but you can do this using approximation techniques like variational EM, variation-based EM. People have used Gibbs sampling, non-parametric schemes like Chinese response process, Indian buffet process, allocation sampler by Niall and Brendan, and then greedy search, and so on and so on. And in terms of model selection, you can use not BIC because the likelihood is not tractable, but some kind of variational BIC. You can use the ICL criteria and so on. So a huge amount of work has been done on this model. And then the double graph model, which is probably more interesting and more flexible. So it's called double graph model, and in some cases graphon model. Basically, it's defined by a function which is called the graphon, and basically which goes from 0, 1 squared to 0, 1. And how does it work? So basically, WUV is the probability that two nodes, I and J, with respective coordinates U and V, to connect. So that's their probability to connect. But the idea, the core of the model, is very similar to the stochastic block model. So you sample some latent variables, and then knowing the latent variables, you use some kind of pairwise information, and then you sample edges. So in that case, you sample for each node I, you sample from a continuous uniform distribution over 0, 1. And then knowing the latent positions, you sample an edge between I and J. So again, a Bernoulli distribution, and W is the probability of a connection. Very interestingly, so this is an example, and again, this model is only defined through the graphon. Very interestingly, there is a connection between the stochastic block model and the W-graph model, and to do this, to illustrate this, we're going to discretize the 0, 1 segment. So, and mainly we're going to consider these random variables. For now, they're not random, but they will be in a minute. So sigma k, they are cumulative sums, so of cluster proportions. So sigma 1 is pi 1. Then sigma 2 is pi 1 plus pi 2, and so on and so on. So because you're sampling from a uniform, continuous uniform distribution over 0, 1, the probability of being here is exactly the size of the interval, so pi 1. So basically the probability of being in cluster 1. then the probability of being here is exactly pi 2, the probability of being cluster 2, and so on and so on. So with this discretization, the sampling scheme is exactly the same as a stochastic block model. You build up some clusters. And then we use this variable here. So how do you define the graphon for a pair UV? This is basically a block evaluated. So this variable here gives you the cluster of U, so the right segment, and this gives you the segment of V. So you know in which class you are, and then U and V connect with this probability. So this is simply a blockwise graphon. So the size of your blocks are related to the size of the clusters, and then the height of the block are related to the probability of connections. So how does it work in practice? Well, you've got a network, and you could say, okay, so I'm going to use an algorithm for the stochastic block model. First, I estimate the number of clusters using model selection or non-parametric schemes, and then I estimate alpha and pi. I build this graph, and I see this as an approximation of the true hidden graphon model. So that's one way to go, but you can do more complicated things, far more complicated things, and there are people in that room who did very interesting work on this. Very interesting work. So again, this is not new, but it has received strong attention in the last 5 years. That's quite impressive, actually. So what we want to do here, going back to that picture, this is not, we're not happy with this because it's too sharp in terms of approximation. So we're going to go to a Bayesian framework, and we're going to try to put some uncertainty here. So if you think about a Bayesian framework for the stochastic block model, you would introduce conjugate priors. So this is exactly what we did in the first paper. So for you're going to do something quite simple. For the cluster proportions, you're going to use the Dirichlet prior. And for the connection probabilities, you're going to use beta priors. Then you use the variational Bayes EM algorithm to approximate the posterior. So here, for example, here you approximate, so Y, this is the adjacency matrix, so you approximate the posterior distribution of pi as a Dirichlet. And here you've got a hyperparameters which is updated from the data. And then for the connection probabilities, you've got a beta, and again, depending on some hyperparameters. So very standard, a simple VBM algorithm does the job. And along the way, you also can get an approximation of the posterior probability of model K, so K clusters in the model. So why is it interesting in practice? Because if you go back here, remember, the grid is based on pi. So if you can, now pi is a random variable, so you've got some uncertainty on the grid. And rho, the connection probabilities, you also have some uncertainty. So the VBEM algorithm clearly provides an approximation, although there are some consistency results. But here we see it as an approximation. Then from this approximation, you can integrate all of this exactly. So in particular, the Dirichlet here over the grid can be integrated out exactly. And this gives you something like this. So you pick up 2 points U and V, and then this is the expected posterior distribution of the graphon at point U and V, given the data, and for now, the number of clusters is fixed. So this is, I'm not going to go into the details, but basically this is a sum over these terms here, which are joint cumulative distribution functions of Dirichlet distribution. The key point, the key idea to prove this is that if pi follows a Dirichlet distribution, if you do cumulative sums, as we do to build the sigma 1 and so on, you would still get a Dirichlet distribution. And then from this, you can integrate the uncertainty. And that gives you something like that. And I'm going to show you how it works at the end of this talk on real data. So now let's use this idea This was for a fixed number of clusters, but obviously you can do Bayesian model averaging, and you marginalize this over the posterior distribution of a model with k clusters. So this framework basically is based on the idea that you want to approximate a graphon as a Bayesian model averaging of stochastic block model with increasing number of blocks. That's the idea. Now let's go back to our problem. So this is the logistic regression model. And this is the model that, people have used very similar models for a long time. So you've got some covariates and then observed data, outputs, binary outputs, and the real vector here. So as Peter Hoff said yesterday, this model that we are going to call H0 assumes that all your vertices are independent. And in practice, as we saw yesterday, we had nice pictures illustrating this. This doesn't work in many cases. If you look at this carefully, this independence assumption does not work. There are some complex dependency between the vertices and so on, in the creation of edges and so on. Now, let's talk about this more precisely. When you do logistic regression, in practice what you do is that you condition something, a likelihood, on the covariates. And this is quite important for the idea behind. So basically you're going to maximize a likelihood of the adjacency matrix given the tensor. So you condition the covariates. So this notion of dependency between the vertices is very much related to what you put in your covariates. And now, as you're going to see in this, at the end, I give some results on real data. If we had enough covariates, let's say quite a big number of covariates, then you might assume that because you put so much information here, then at the end of the day, you might get some kind of independency between the vertices. The covariates explain everything. So that's pretty much the idea. Is that the case? Do my covariates explain entirely the construction of the network? Or is there something else? Is there some kind of hidden structure, something that we don't explain? And in that case, that means dependency. So we're going to go to model H1. And here, this is very much related to what Pierre said. If there is some kind of dependency, you would get some kind of extra terms related to pairwise information. This accounts for dependency between the variables. So you could add, for example, a row effect, column effect. You could also add some kind of distance, like we had for the in the talk of Adrian, some kind of measure of a distance in a latent space. You could also say, I'm going to use some kind of factor models, as we had in the talk of Peter Hoff, and so on and so on and so on. So we are here in a hypothesis testing framework, and you've got a real data set, and you want to decide whether or not your H0 explains your data. So we tried to do this, but it was a little bit too hard. So we used this idea that we had in the previous paper. So we're going to replace this term, which can be basically anything. It's a very complicated term. We replace it by this term here. So this is the idea of constructing blocks, actually. So here you've got this depends on the number of clusters, and again this is within the logistic. So this is not exactly a graphon, but if you remove this term, you've got j of phi. This is a graphon, and then here if you remove this term, j of this is exactly a stochastic block model with a fixed number of clusters. So hypothesis H0 corresponds to model M1 exactly, because here if you've got only one clusters, then this terms here boils down to only one alpha. So if you've got one cluster in this corresponds exactly to H0. So no problem in that case. And then unfortunately we couldn't work with H1, so we're going to replace H1 with H1 prime as the union of all models except model 1. So every stochastic block model basically except the one with one cluster. So now I'm going to go a little bit faster on this. We consider Bayesian framework as we did before. The set of parameters is here. And the key point is that we have transformed the hypothesis testing framework and we have moved into a model selection problem, basically. So, and in that framework, we're going to see the priors in a minute, but in that framework you could try to do to make decisions using base factors and posterior odds and so on. In practice, we use this term. So given the data, how likely is model H0? So we consider some simple priors. We assume that this is the set of parameters. We assume factorized distribution. We assume the same probability for the two hypotheses, so H0 and H1 prime, 1/2. And then the key point is that model 1 gets 1/2, but that then H1 prime, this is all model except 1. So all of these models are going to share uniformly this 1/2. So they split this probability for the different models. And then we're going to use something very standard for logistic regression. So we're going to use some Gaussian distribution for the regression vector, Gaussian distribution for the bias terms, and so on. Nothing more to say here, just to say that again, for the cluster proportions, we're going to use Dirichlet prior. And then the key point is that within this Bayesian framework, we had to add an extra layer because working with Gaussian was not sufficient. You have a very high price to pay when you set this inverse term here. So we had to add an extra layer, and in practice we used gamma priors. So what does it mean in practice? The prior over beta, that involves a marginalization over eta, and for alpha this involves a marginalization over gamma, and this class of distribution has been studied a lot in regression, and this corresponds to generalized hyperbolic distributions. In that case, you need the marginal likelihood to make a decision, to compute your base factors, and so on. Unfortunately, it's not tractable. It's very complex. You've got strong dependency in here. So you consider Bayesian framework, standard variational decomposition, and usually you're fine with this. This is the case for the stochastic block model. You're fine with this. But in that case, because we are using a logistic regression, you can't get analytical expression through the algorithm. So you need an extra layer of approximations, and we used a bound that was proposed by Michael Jordan for Bayesian logistic regression. This is given here. Basically, this is the log logistic. It decomposes into a linear term and then a function which is concave, not in x, but in x squared. This allows you to build up a bound. And you've got now this new term, xi, which allows you to place at the right place the lower bound. So this gives you something like this. So you can fit your function with the bound that you prefer. So this is the marginal log likelihood. This is the variational, the global variational approximation, and this is the so-called variational global and local approximation. Okay, so I'm not going to go into the details, but just to show you how it works. In practice, if you condition at some point, you're going to get a sum over all pairs of vertices. And for every pair of vertices, there is a term that you can't compute. There is an expectation that you can't compute. So we're going to use that bound for every pair of vertices. And you can set this psi aj term to get the better bounds. And then, so going back here, Ideally, we would have worked with this. This is still not possible, so we work with this. You do functional maximization with respect to Q to approximate the posteriors, and then you maximize this with respect to Xi to get better bounds. And you alternate convergence of the lower bound. Okay. And that gives you an approximation of the posterior. And again, so an approximation of the posteriors, and again, this gives you an approximation of the marginal likelihood. And from this, you get an approximation of the posterior model with K groups, and so on. So you can compute your base factors and so on with such a procedure. And also, a very nice result in practice, when you do this kind of estimation, you can remove the regression term and focus on the residual term and try to estimate, as I showed you before, the residual graphon term. So how does it work on a bit of simulation? So we have got this term here. Rho controls the density of the network, and lambda controls the curve of the graphon. And keep in mind that for lambda equals 1, basically this is the Erdős-Rényi model. So this function boils down to a constant. So H0 basically. For lambda equals 1, this is H0. And then we build up some covariates in dimension 2 and so on. And we use the methodology I showed you. So you've got several graphs. This is for networks generated with 100 nodes, 150 nodes, and for various density settings. And then for each graph, you've got here the lambda term. So again, lambda equals 1 means that we are exactly in H0. And as lambda increases, we go towards H1 or H1 prime. And then here, in all graphs, this is the approximate posterior distribution of H0. So basically, the right answer, if lambda equals 1, the right answer is to say 1. And then, as lambda increases, you would need to say something that goes very quickly towards 0, to say no. There is some kind of dependency. I reject H0. And as you can see, this it takes some time to get good results in that case. We would have expected probably sharper results with a better algorithm. But as you increase the density, or if you increase the number of nodes, you get very, very good results very quickly. So you detect very quickly that H0 should be rejected. And then finally, we go towards real data sets. We've done a lot of experiments. This is just a few results to illustrate how it works. So many data sets, so the blog data set that you saw yesterday, of political blogs, tree network, karate club network that you know probably this one too, and so on. You have got the size of the network, the number of covariates, and the density of the network, and then the approximate probability of H0. And as you can see, the two first ones, the blog and the tree networks, were rejected. So that basically say the logistic regression model does not work for this model. There is something else. There is some kind of dependency, and the covariate information that we have is not enough. And for these remaining ones, and in particular this one, the Fox-Dixon high, we've got something which is extremely close to 1. And so this means, in this data set, the covariates, you basically describe the relationship between students. And in terms of covariates, we know the grade of the students, the race, and the sex. So basically what it means is that if you know this information within this data set, you know everything on the relationship between students. There is no heterogeneity, there is no kind of dependence behavior and so on. And finally, final results, you can get the approximation of the graphon remaining term. So on the left, you've got without covariates. This is just a graphon estimation as an average of stochastic block model. And on the right, the same with the covariates. So this is for the blog and the trees. And as you can see, on the right, this is not constant. There is something else, something that we don't expect. don't explain, sorry. But still, you see that as we had covariates, the graph from term gets smoother and smoother, but still, there is something left. But for the remaining ones, if you see here, adding the covariates, there is nothing else. And I'm done here.
Question or two? You can.
Thank you for a very interesting talk. Just a technical question. The 4 Dixon high. So I only know the 4 Mesa high, which I know is generated using a model. So how is this data set? So it's the 4 Dixon high. Is that generated using a stochastic block model? So how is the data set comprised?
I'm sorry, I don't get the line.
So one of the data sets, you got the posterior probability 1.
Yeah.
But I know that some of these, well, I know the for Mesa high data set, which is not the one you use. I seem to reflect that is generated using a model itself.
I think it's based on an ergon or something like that.
A fit on a stochastic block model on a school data. So I wonder whether this data set was also based on a...
I think it's based on a simulation, yes, at some point. Yes.
From a stochastic block model?
Yes. Not a stochastic block model, I think it's based on a ergon. It's based on an ergon.
It might be interesting to...
In the details, I don't know, but I know it's based on a simulation. Yes.
One more?
Yes, so your covariates are the covariates for each pair of
Yes.
the nodes. For example, students, you have covariates like a grade or a sex, which is covariates of the individual one.
Yeah.
So wouldn't it make sense to add them as a kind of linear term? I mean, when you take a stochastic block model, that means you have kind of hidden covariates. But if you have known covariates,
you could add them up. You could add these terms on the vertices in the model. You could try to do this. In practice, what we do is that, for example, we do the absolute difference to put covariates on the edges.
okay.
You could think about, but yes, we could think about adding a vertex effect or something like that within the model.
Row and column
Yes,
effect,
yes,
let's say.
yes, exactly.
Yeah, because there's an absolute difference may be reasonable in some cases, but in some cases it may
Yes,
rather be
and then you
additive
have to
or-
make a choice, and then okay, I do agree. Yes, yes.
Okay, let's thank Pierre again.